My name is Vinay Rao. I'm the CEO of RocketML, and Santi is our co-founder of RocketML, and he and I will share this talk. Before I get to my topic, which is around semi-supervised learning, which at this moment is a bleeding edge research going on in that area, let me quickly introduce ourselves. We are a startup of high-performance computing experts, and we are on a mission to bring HPC and supercomputing capabilities to data scientists and in the enterprise. It's all packaged, all those technologies are packaged as a SaaS product. So with that introduction, let me jump into our topic. We're going to split the topic into two sections. I'll cover the first section, and I'll go through the survey of machine learning methods. It's an important setup for the deep dive that Santi will take you through. One such methods for one particular problem, which is anomaly detection, where labels are a problem to acquire. So I'll make two basic points about machine learning so that we're all on the same page. Machine learning basically is a two-step process. There's an offline process, which we call training process or learning process. And then there is a decision process, which we call inferencing process. And there are a lot of other techniques that are coming up trying to merge the two, be it reinforcement learning or continuous learning. There are concepts coming about, but they're still in very early phase of the research. For all practical purposes, it's a two-step process. Our talk will focus mostly on the offline part of the challenge. And the second point I want to make is that machine learning is basically iteration on iteration on iteration. So a data scientist has to run dozens and if not hundreds of iterations to get to an optimum solution. Whether it is in the pre-processing phase or in the training phase, it's iterative process that's where you need the speed and the scalability factors come into picture. So let's jump into the machine learning methods. So the two most used methods are fully supervised learning and fully unsupervised learning. I add the word, mostly people use the word supervised learning, I add the word fully to contrast against semi. And there are fully unsupervised learning. The idea here is that you train a model to perform classification regression with labeled data. That's the idea here. Whereas on the other extreme, you don't have the labeled data and you try to make sense out of the data. Now, a lot of new methods are coming up in the middle because the problems on both extremes, and which is where we think the future of the AI resides, because they address the problems of the current methods. So I'll give introduction to each of these and set it up for Santi. So you take the future of the machine learning, it addresses three problems that current machine learning methods have, which is the total cost. The total cost definition is that you have labeling cost, you have the machine learning engineer or data scientist cost, the human cost. Those are the two human costs. And then you have cost of compute, which depending on the method you're using can go through the roof. And then you have the biggest piece of the cost, which is the opportunity cost. But the opportunity cost is a little difficult to nail down because it touches upon the other two aspects of the machine learning. That's the first metric, a very important metric. And in today's machine learning world, everybody's chasing accuracies. And my point is that it's not everything. So let me illustrate that point with the next two metrics. Second metric, I call it social accountability metric. A lot of the times in the industry, people use the term interpretability, explainability as a way to describe social accountability. And the example I can give is that if your application is in the medical field, where a human life is involved, then you're highly accountable. Or in a regulated industry, you have to be able to explain why your model declined a loan to someone who applied for a loan. So that's that's on a scale of not important to very important and essential spectrum. And each application have to make those decisions in terms of how important that particular metric is. And the third metric is the robustness aspect of it. Inherently, machine learning is not robust if you want to achieve higher and higher accuracies. So it is a trade-off metric. And if, again, it's dependent on the application, if the application requires you to have high robustness, for example, in a self-driving car application, you have to have very high robustness, then you have to balance your accuracy against those robustness, okay? So this is a better way to assess the value of a method than it is the accuracies in, every month 10, 20 papers come out that claim to be doing better accuracy models than before. So it's important to keep that in mind. Again, further building on the point of accuracy is not everything. Machine learning is essentially an ill-posed problem, and let me try to explain this chart. On this axis, you have the accuracy. On this axis, you have the robustness. And if you go to the extreme end of the robustness, you're giving up accuracy. And if you go to the other extreme, you're giving up the robustness. And so you have to select where you want to be, your optimum point when you're coming up with a machine learning technique. Okay? And usually you can assess them with those three metrics. So I'm going to go into explain a few methodologies. Techniques are increasing in number. I'm not going to cover everything. I'm going to cover maybe 4 of them. This one is fully supervised learning. You probably learned about it. Let me just repeat for the sake of completeness. You have sample. Sample means you have one image or one text tag, one line of tabular data. That's what sample means. And then for every sample, you have to have a label. That is fully supervised. And you use the label and put it into learning algorithm, which is called model training. And you iterate the parameters within that learning model to come up with an optimal model. You validate it, accept the optimal model, put it into inferencing, and test it on new data, and you have a solution. That is a production grade solution. That's the flow chart of a fully supervised learning. The problem with the fully supervised learning, the best example of a fully supervised learning is deep learning. There are other ways too, but deep learning is the most popular one. And the problem there is, again,
conform to a notion of normal. And the challenge is to find the boundaries between what is normal and what is an anomaly. And it's a lot of applications in cybersecurity, fraud detection, predictive maintenance, and so on and so forth. And this snaps to the problem that we've been talking about, that is the process of labeling anomalies itself can be expensive. But there can be very minimal data that can be available to solve this anomaly detection problem. So that's the basic definition of anomaly detection. And there are different types of anomaly detection problems that people run into. One is point anomalies. That is, when you have a time series data and you're looking at some mean and something may be off. And that kind of falls under point anomalies. There are contextual anomalies. That is, based on the current context, is certain event or certain action is an anomaly. It may not be an anomaly in a different context. So there are contextual anomalies. And there are collective anomalies. That is, a group of events together may be not conforming to normal. So in problem, you need better and faster solutions to just do KNN itself, because that's where the majority of the computational complexity is going in. So this is basically where the problem hits. There's a big data problem. That is, when you're working with millions or billions of network events or millions of images, you have to fit your problem into your memory. There's a classic problem. Every problem hits into a memory problem. And there is a data movement problem. You have to get the data from the disk, move to RAM, move to cache, and then you figure out whether you have to move to CPU or a GPU. So there is a lot of data movement problem that's coming in. So most of the implementations of KNN that you find in open source or commercial, you basically use single core implementations of KNN. So they are very slow in actually building the graph itself. So if your problem goes beyond RAM, it basically takes ever and ever to actually build a graph. So to mitigate that, we need to go to a cluster computing solution. That is, you want to be able to make use of commodity software or commodity hardware, put all of them together to get a really large memory footprint or RAM footprint and be able to build your models, build your KNN faster. So when you're going for a cluster computing implementation, while you're solving the RAM problem, that is you have more memory, you actually add a new problem, which is how do you communicate between your machines? And basically, how do you optimize your communication patterns? And how do you actually distribute your algorithm itself so that it can do it on more machines? So that's basically an optimal implementation that we had to come up with to address these iterations problem. And we tried to compare our implementation of KNN with I think there's only one solution method we could find available with SageMaker. And on the left-hand side, what I'm showing you is the runtime. That is, for the KDD network intrusion data with 1 million samples and 81 dimensions, we were looking at the runtime. That is, how long is my training time to build a graph, right? With k is equal to 10, and plotted the runtime with respect to the number of cores we are using, because that is what we pay for, and that's basically what is in our control. As you can see, we can actually, if you do an optimal implementation of these algorithms, you can, one, get really fast graph building optimum. That is, just using one core, we were able to actually build a KNN in less than 300 seconds, while on SageMaker for 8 cores, we basically take almost double the time. Not only that, as we increase the number of cores, the scalability, that is, the amount of time it takes to build the graph, actually reduces pretty linearly. So this is the speed up that is kind of plotted here. That is, the blue line here is the optimal scaling. That is what you strive for. That is, you increase your number of cores from 2 to 4. You want your problem to get done twice faster. And in a lot of embarrassingly parallel problems, you can actually achieve this because there is no communication between the machines. But once you have problems like KNN and other things, there is a communication overhead that basically explains why this gap is. So, but the comparison here is between RocketML and SageMaker. We could actually see that the scaling is much better and linear compared to SageMaker, which is basically very flat. So 10 times faster than SageMaker and optimal strong scaling. So going back to do a practical anomaly detection, you need 3 components. One is a good algorithm that is interpretable and robust, that is k-nearest neighbors. You need to do feature enhancements, either using SVD or ensembles or encoders or pre-trained models. And last but not least, you need to have really fast, scalable implementations so that you can do iterations and get your models to production. So to conclude, learning is possible with very few labels, and it can be interpretable and robust. And semi-supervised learning requires experimentation and rapid iterations. You need to be able to iterate with different parameters. And fast, scalable algorithms are needed to provide cost-effective and timely solutions. So this work is sponsored by National Science Foundation, and we plan to open source some of this work and also publish. So if you're interested to talk more about this, we'll be available after the talk. And thank you very much.